Let's work through an old exam question about the photoelectric effect. This was the worst answered question in this exam, so it's really important that we get to understand how to get these easy marks. You should at this point pause the movie and try to answer the question yourself. Download the questions from the link that I'm providing below, and while you're doing so, remember to like and to subscribe. You can also find movies like this and on many other topics from my website, so please visit www.learnscience.co.za. And another thing that you should maybe do before we get into answering this particular question is visit that link over there, which gives you a bit of background about the photoelectric effect, a really interesting topic of science. See you in a bit. We're given this graph and we're asked some questions about it. Let's first make sense of what the graph is saying before we look at the questions. We can see that the x-axis has Vmax squared as its label. And we must multiply whatever values are here by 10 to the power 12. Bear that in mind. The unit, of course, is that of velocity squared. Velocity, meters per second, and now velocity squared, meters squared per second squared. So that refers to the maximum velocity of the emitted electrons. This tells us about the light, the energy of the photons. Obviously, these numbers here must be multiplied by 10 to the power minus 19. Don't forget that when we get to the calculations. The greater the energy of the photons striking the metal, the greater the velocity squared, the greater the velocity of the emitted electrons. We notice it's a straight line, and that's also not surprising. Why not? What does velocity squared bring to mind? Kinetic energy's formula. We know that the maximum kinetic energy of those emitted electrons is equal to half the mass of an electron multiplied by the maximum velocity squared. So then it really isn't surprising that we're getting a straight line, because we can see that the kinetic energy of those electrons emitted at maximum velocity is directly proportional to their velocity squared. But why does this then not go to zero? Because in direct proportion, this graph should cut the origin, and it doesn't. There's an intercept at 7,48 times 10 to the power minus 19 joules. What is the meaning of that? Well, this is the energy of photons, which would cause emission of 0 meters squared per second squared. So the velocity squared of such electrons would be 0. In other words, the velocity would be 0. In other words, their kinetic energy would be 0. They wouldn't be emitted. So this is a threshold. It's a cutoff. At energies above that, we get emission. At energies below that, we do not. So what do we know that is a threshold, a cutoff? Often it comes to your mind that we must be speaking about threshold frequency, because the word threshold is inside that term. But careful, because this is not speaking about a frequency, it's speaking about an energy. But what is the energy associated with threshold frequency? Work function. What does that mean? That means that this is the amount of energy that a photon needs minimum to emit electrons from this particular metal, silver. Any more than this amount of energy then goes into increasing the kinetic energy of the emitted electrons. So we know that this value, remembering to multiply by 10 to the power minus 19, is the work function of this particular metal, and that is the answer to this question. We're then asked to justify that using an equation. We know that the energy of the photons is given to the electrons in two forms, we could say. Some of it is needed to overcome the attractive force holding the electrons. Now, in the case of the surface electrons, that amount of energy is called the work function. And that is required to pull those surface electrons away from the attractive force that the metal kernels supply. And then any excess goes into kinetic energy. And since here we are speaking about the surface electrons, that's the amount of energy needed to pull the surface electrons away, we are speaking about the kinetic energy of those surface electrons, which is the maximum kinetic energy of all the electrons. Obviously, the deeper electrons, they would go off with a lower kinetic energy than the maximum ones for the setup, and they would also require more energy to pull them away. Now here we are speaking about when kinetic energy is zero. V squared is zero. Well, that means kinetic energy is zero. So then that part of this equation goes away. Well, let's keep it there, but just make it zero. And then can you see that the energy that the photons supply, all of it is needed to overcome the work function. There is none left over to go into kinetic energy. So this shows us that when we find that the kinetic energy of the emitted electrons is zero, in other words, there isn't any emission, but it's just the cutoff, slightly more energy of the photons then causes emission, so we're at the threshold, not below the threshold, then the energy of the photons equals the work function. That's a way of determining what the work function is of that particular metal. Next, we're asked what physical quantity is represented by the gradient of this graph. Is extremely poorly answered in this exam. And to help us, it's really very simple. We just have to think about what gradient means. And we know that gradient means rise over run. And what is rise? Let's take this little triangle here as an example. What is rise? Rise in this case is change in energy, difference in energy between there and there. And what is run in this case? In this case, it is change in V squared. In other words, the gradient of this graph is the difference in energy per the difference in V squared. And doesn't that look familiar? Remember this equation over here. If we would rearrange this, we would find that EK divided by V squared is equal to half m. So the gradient of this graph gives us half m. Half m of what? What are we speaking about here? The mass of the emitted electrons. Well, all electrons have the same mass, so the mass of electrons. Of course, it would be half m, but they're asking us which physical property, and the physical property is the mass of an electron. Now we're asked to calculate what x is. I'm going to make use of this equation and substitute values that we know from the graph. So let's start off substituting into this equation. Remember, we're trying to find out what x is, what v squared is, when the energy of the photons is this value. Now, we're not yet going to find out what v squared is. We're first going to find out what EK max is, but can you see that that is related? So we're going to get there eventually. So we use this equation. The energy of the photons is equal to the work function, which we know from over here, plus EK max. And so we substitute that value 11,98 times 10 to the power minus 19 joules into E there. The work function we know is 7,48 times 10 to the power minus 19. And we need to find out what EK max is. So on our calculator, we do this calculation. We take this one across. So it's 11,98 times 10 to the power minus 19 minus 7,48 times 10 to the power minus 19. And that gives us EK max. And the answer is 4,5 times 10 to the power minus 19 joules. Don't clear your calculator. What does that mean? That is the maximum kinetic energy of the emitted electrons for this energy of the photons. Remember though, we weren't asked to find EK max, but rather x, in other words, v squared. So we have to continue. So that is equal to half the mass of an electron, which we can look up on our data sheet, times the velocity squared, which is what we're trying to find out. We go to our data sheet. We find that the mass of an electron is 9,11 times 10 to the power minus 31 kilograms. Very light, of course. V squared is equal to, and we'd already found that previously. So now we just need to do some algebra to solve for V squared. Notice we don't need to solve for V because we're trying to find X, which is V squared. V squared is equal to this number divided by this. And when we divide by a half, it's the same as multiplying by 2. So we can just simply go like this. 4,5 times 10 to the power minus 19 divided by the mass of an electron. We have this value already on our calculator. Divide by 9.11 times 10 to the power minus 31 multiplied by 2. And we find that the answer is 9,879. We can round that off to 9,88 times 10 to the power 11. And make sure that you give the correct unit, which is given over here. Meter squared per second squared. Last question. We're asked, what would the difference be if we use a brighter light? How would that affect the gradient of the graph? And how would that affect the rate at which electrons are emitted by the light? Well, the first question is actually very easy if we've realized that the gradient of the graph tells us something about the mass of an electron. And the mass of electrons are always constant throughout the universe. So we can't go and change what the mass of an electron is by simply using brighter light. So clearly, the gradient of the graph is not going to be altered. Stays the same. Now, what about if we increase the brightness of the light? What will that do to the rate at which electrons are emitted from the metal? How does brighter light compare to dimmer light? Brighter light has a greater density of photons than dimmer light. More photons will hit the metal surface per second with a brighter light than with the dimmer light. Now, as long as each of those photons carries sufficient energy to overcome the work function of the electrons in that metal, then the more of those photons you have striking the metal, the more electrons can receive enough energy to be emitted, and therefore the greater the emission rate. So for that question, increases would be the right answer. And that brings us to the end of working through this particular question. I hope you found it useful, and if you did, make sure that you have liked and you have subscribed. And remember that you should leave me comments and go and visit my website. There you can easily find whatever it is that you're looking for, because I've categorized my movies under the different topics, and for the South African curriculum, under the different grades. Until we meet again, happy science learning.